We are now recording. Let's get the slideshow set up from the current slide. But before we do that, you had a question. Is that right? 83. Okay. I'm sort of slow because my eyes aren't focusing well. Okay. So let me get my pen set up. Okay. So this is page 83. This is 2.4 exercises. And which one? Say that one more time. 60. 60. Got it. Okay. All right. Number 60. Oh, yeah. I'm sorry. Well, I'll wait till after I make the announcements and then I forgot to go back and change it. Okay. As soon as we get our projector up, we'll be ready to go. Here's number 60. It says, define g of x. It's a piecewise defined function, and that's x plus 3. That's for all x's less than -1. Okay. Cx, and that's good for all x's between -1 and 2. That includes both endpoints there. And then it's 6. Goodness, x plus 2. And that's good for all x is greater than 2. You have to check and make sure I'm seeing the right things, because it's really a pain to look. I mean, all right. I think I wrote it right. Okay. Now, it says here, find the value for C such that G is first left continuous and secondly right continuous. Okay. Now, I don't know if it's helpful to draw it or not. Do you feel like it would be? No. Okay. We want that. What do we mean to be left continuous? Okay. And that's I have a hard time explaining or describing this without this graph. So would you mind if I went on and did it? Okay, let's go on and do it. All right, let's do this function. Let's see. We'll just use the graph they have here, I think. And it's x plus 3 for all x's less than -1. Well, x plus 3 would have a slope of 1 and a y-intercept of 3. But understand it doesn't go to that 3 because this is only good for -1. So it would have this point down here and actually not even that point either. Okay, but from here on down it has a slope of 1. Okay, you see what's happened there? I hope I drew it approximately the slope of 1. this had continued to the y-axis, this would have been intercepted at 3, right? With a slope of 1, right? I don't have my slope quite right either, okay? Slope of 1, okay? But it doesn't go there. That stops at -1, and in fact, it doesn't even get to -1. So if you go back 1, down 1, and back 1 here, to the left one, then that point is also not on the curve, on that line, but that's where it begins, and then it's, I probably need to, let me try this, plugging in a few points. That might be a little better. Goodness, my eye hurts. This will be -2, and at -2 it's right here, and then -3 is here, and it goes through there. So here's up to that point, but not including that point. Okay? Then it's CX anywhere from -1 less than or equal to x less than or equal to 2. And then it picks up again at x plus 2. Now that would have a slope here, I mean a y-intercept here, but it doesn't go through there. And it's not here either. Again, a slope of 1. But then here at 2, again, it's not there at 2, but it's almost there, and from there it has a slope of 1 upward. Okay. All right, both of my X chromosomes are here. Where are the Y's? Why are they not here? We don't know. All right. We're doing a problem from section 2.4, page 83, number 60. Okay? And what we've done is drawn the graph of g of x when x is less than -1 and greater than +2. Okay. Now, in between here, we want this to be a left continuous function. Okay? That's what the A part is calling for, a left continuous function, which means approaching from the left as x is approaching, say, -1 or even, hopefully, to +2, this is going to be continuous. Okay? From here. Okay? Well, one thing we know has got to be true. When x is -1, we want y to be 2. Right? When x is -1, we want y to be 2. Agreed? Okay. Well, then we know that c times -1 is equal to 2. What do you reckon the c is going to be? -2. Okay? Now, that looks a bit strange, but you see, this thing has a y-intercept of 0, right? Because there is no y-intercept there. There's no b, so it has to be coming here. But if you did that, and that's actually going to be all the way good down to here, okay, then that is left continuous, okay? It's continuous coming here and down to here. So in that case, the c would have to be -2. C is equal to -2. All right. Now, let's do this next part, the B part, in a different color. You pick me a color. Green? Okay. Light or dark? Light. Okay. She goes with light green. Good spring color, right? Okay. In this case, we want it to be right continuous. So again, we want the point here, that point right there, to be 4, right? F of 2 has to be 4 for that to be right continuous, right? So in this case, Cx or C times, there, okay, can't get it to erase. Okay, C times 2 has got to equal 4. So guess what C has to be? 2. And guess what? That just is this, oh yeah, C is equal to 2. That's going to be 0, 0. Again, there is no y-intercept. And 1, 2, 2, 4. So that's going to be the line that makes that this continuous, a right continuous function. Coming from the right, it is continuous. Okay? Oh, and actually, this continues down to here. Okay? So, the C of minus 2 makes this a left continuous function, filling in the dot there, and then it just has to go wherever it goes. There, you see, has to be a plus 2, and that, sure enough, makes it intersect there, so it's right continuous all the way down to here. Okay. Now, in neither case will it ever be continuous everywhere. It's, in the first case, here to here, and then an open circle here. It's not left continuous. It's not right continuous there, but it is left continuous. Here, it goes up to here with an open circle there that picks up here and goes there and bends there and makes it right continuous at that point. Okay, does that answer what you have? A little, okay. Which was the problem you were asking about? Okay, which one? 6? 2? Oh, okay. Yeah. Yeah, it's just not, it's not a continuous thing, but that the function exists. And of course that would have to make it continuous as well. So now this doesn't have to be continuous. Number 2 doesn't have to be continuous. All it has to be is that the limit exists. Okay, and so frankly, that middle value in there is immaterial. The 10 is just a value there. But remember, for the limit to exist, all that's required, I can't really draw it on this one well, but let's just say, for the limit to exist, let's just say that this one here had a value f equal -1, had a value at, yuck, where does my pen go? It was still there. Okay, f of -1, it would be 4, but then, and you see we knew nothing of what was going on over here, okay? So, but we knew something was happening here, okay? Even this, though this is an open circle here and has this value up here, that doesn't matter. As long as the limit exists coming this way and that way, the limit exists, even though the value isn't the same. This would not be a continuous function, but it would have a limit, okay? So all you have to do is find the value C, which makes sure it intersects at that same point. No matter what this 10 is on here, or that value is up here, that's out of the question. For the limit to exist, it can be an open circle right here. All you require is the limit from this side and the limit from that side has to be the same value. Does that answer? But you do it in a similar way, but you just, that 10 is just out to lunch. It's a removable discontinuity, by the way. Number 6 now? Okay, wait one minute. Find 6. Okay, here we go. And both of you did get your test right. Yeah. Okay. Number 6, what? Yes? Right.
But I didn't know how to tell if they were removable, jump, infinity, or no.
Okay. Let's give some examples of that then. If it was removable, let's just say this picture I just drew here. Okay, it comes up here, it's an open circle, something else up here, but then continues over here. That's a removable discontinuity because you can just change that value to here and it would be continuous. Okay? Now, for it to be a jump discontinuity, that would be like this one. It comes up here, has an open circle here, then a solid circle here, it goes. There's no way you're going to make those two ever the same. That's a jump discontinuity. Or this would be a jump discontinuity. No way. This is down here, that's up there, there's no value you can put in to remove that. That's a big jump. Okay? Now, infinite would mean, say this function was doing something like this. And even though this one's coming down like that, they're never going to meet. They're going to infinite. That would be an infinite. And then none of these would be one. Remember those crazy functions that do like this? Yeah, it would never, ever, ever, ever meet. That would be none of these. That is one example.
And my last question is on, I think I had found an example in the book from number 9.
Okay. It's all right to go and erase this number 60 that we just did. Okay. Okay, well, if you find it later, you can ask me later too. Okay, Wednesday or whenever. Okay? Any other questions before we get going on today's? Okay? Where we left off last time was talking about computing limits, okay? And using the definition. The graph of a linear function, and here is the graph. I'm going to blow this up for, well, let me do a couple of things first. First, go back to a dark color. And then, secondly, we'll blow this up. Now, this is an example of a linear function. Now, what do we mean by a linear function? It's one of the form f of x is equal to mx plus b. We were just doing a couple like that. Where b is the y-intercept, that would be here, looks like about 1.5, something like that is a guess. And here's m would be a slope. Well, let's see what the slope would be here. If this is indeed 1, when you go over 1 here, it looks like it's up 1. That looks like about a slope of 1. It may be a little off, but something like that. Okay? So, that is an example of a linear function. Any old linear function. Okay. Where m and b are constants, the slope is m, the tangent line at any point coincides with the line itself. Okay? And that's shown here in this figure. So it's hard to see where the tangent line is because it's the same. If this is a straight line, pick a point here, the tangent to that line is that line. Every point, the tangent is the same line. So they do coincide. Okay? Now, that's graphically. Okay? We should expect that the derivative, f prime, oops, get out of here. The f prime is equal to m. Okay? Because the slope of the tangent line is the same as the slope of the line itself. Okay? So let's see if that's indeed true. What was our definition for a derivative? F prime of a. Do you remember that definition? There were a couple of different forms of it. Do you remember what they were? The limit as x approaches, okay, I'll let you give me the formula for it. F of what? Okay, my hearing's bad, so you could say it again. Right. Okay, and call out to me the difference question because there's two different forms for it. See, if you go back to the definition of derivative on page 114, there's either the equation 1 or equation 2. Okay, if h approaches 0, that's what I needed to know. Okay, of f of x plus h minus right? Okay, over h. Perfect. Okay, that's your definition. Okay, so with this being your function, then we need to calculate what f of x plus h is. Right? And what would that be? Okay, f of x, yeah. Okay, no, okay. What we're doing, here's your f function. F is equal to mx plus b. What we're doing is figuring out what f of x plus h is. So instead of x, we put in x plus h. Instead of x here, we put in x plus h, and what does that give us? M times x plus h plus b, right? I started to put a for some reason. So what would this be? This would be mx plus mh plus b, right? All right, so that's what we put up here. I'm going to leave off the limit for now. The f of x plus h would be mx plus mh plus b minus f of x. Well, here's f of x right here. So that'd be minus mx plus b, right? F of x is this thing right here. So instead of f of x up there, we put mx plus b, minus, right? And that's all divided by h. And that's taking limit as h approaches 0. Okay, we'll get back to that later. Okay, I can't read my writing here. That's a plus there. For some reason, the plus didn't come through. Okay, so let's do what it says. That's the limit as h approaches 0 of mx plus mh plus b minus mx minus b, right? Distribute that minus sign across the parentheses, right? Okay. Well, here you have an mx minus mx. That adds to 0. Oh, and this is all divided by h. And here we have a plus b and a minus b. That adds to 0. So this gives us the limit as h approaches 0 of all that you got left is m h over h. And guess what the h's do? They go out. So what's our limit? M. So the first derivative, sure enough, is f prime of a is equal to m all values of a. Using the definition. And you could have used either definition you wanted to. That's why I wanted to know which one you were using. Either one of them would have worked. Okay? And you've just proven that the derivative of a linear function at f equal a, at x equal a is m. The slope of your tangent line is the slope of the line. And that's why the tangent line is the same as the line everywhere for all a. Any a you have up there. Because the a disappeared. You didn't use it anywhere either. And actually, I'm sorry. I sort of botched this up too. I was thinking the first definition. Here, instead of a and x, we put our a's in here. Sorry, I should have done that. But it all works out the same. Okay? Because you're evaluating it at a. So this would be a plus x, a. This would be m_a, m_a, m_a. They go out, m_a, they go out. And it all works out the same. It's just you put it instead of, down here too, sorry. That should have been an A and an A and an A. Okay. I wasn't paying attention. Okay. Yeah. All worked. We're just supposed to plug in A for X. I left the X's, but they all disappeared just like they did otherwise. Well, that's supposed to be an A up here. It looks like a C to me, so let me make that look like an A also. Okay. Good. All right. So we have done it, and they do it. They use the other definition. It's fine. Either one of them works. And I can't see it now. Oh, I'm sorry. I turned back the page. No, they use the same definition you did. F prime of a is f of a plus h minus f of a, the limit of that. Yeah. All right. Now, one other little deal here. What if that slope is not +1 or -3 or plus I/halves or whatever? But what if that slope happens to be at 0? Then guess what we've got there? If f of x is equal to b. In other words, that mx, the slope m is 0, so all you have is a b. Then this is what you, whoa. Okay, they have the slides out of order. Okay, this is what that looks like. The derivative of a constant function, fx equals b, where the slope is 0 now, that looks like that b is about 3.5, whatever it happens to be. Derivative of that constant function, f prime of a is equal to 0. Well, what's the slope of a constant function? 0. So yeah, we just did it by the last. Was someone else trying to get in there? Okay. So that also is 0. Okay. So in summary, let's go back to this. And here are two really good little rules to keep in mind. This is your theorem 1. Derivative of a linear and a constant function. If f of x is equal to mx plus b, that's in your linear function. It's a linear function, and f prime of a, the derivative of f of a is no matter what the a is, for all a, it's always m. Now, if this f of x is equal to b, in other words, x is equal to 0, meaning which x being a variable, m would have to be 0, and that's a constant function, then the derivative of that one is what its slope is, which is 0. L prime of a is 0 for all a alpha. Okay? You can go back to the definition and show that's true as well. But we really just did when we showed it was equal to m, and if m's 0, that's equal to 0. So let's do example 4. Does example 4 have no. It does not have a slide, I don't think. Let's see, I don't believe this is, yeah. No. All right, we'll do it on this one. Example 4. Find the derivative of f of x is equal to 9x minus 5 at x equal 2 and x equal 5. Okay? It says find the derivative of that. Now, you tell me what to do. What's that? Okay, plug it in what? Okay, x equal 2 and x equal 5 there. That will give you the f values, right? The y values. What we're looking for is what is the derivative of that. Yes, exactly. A would be 9, B would be 9. It doesn't matter. It's a linear function. The derivative is the slope. Okay? M equal 9 in both cases. That's it. That's all you have to do, okay? Because it's a linear function. And the last theorem, we just proved it. Now, you can go back to the definition and do it that way. You'll see it comes out 9 in both cases, okay? But why go through all that? We've already shown. Okay. Now, that was pretty easy, right? Let's do example 5. This is not example 5. They don't have, okay, obviously in the old edition, they didn't have an example 5. Y'all both have the new editions, don't you? So let's do them here. Determine the derivative of function f whose graph appears in the figure, and yeah, we don't have a figure. Let's see if I've got anything on the graph. Let's use this one, okay? Let's clear this out of the way. And let's use this graph. Might have to expand it a little bit, but it's not going to be too bad. Now, the only thing sort of bad with this is, and maybe it's just my poor vision here, but that's one here, and that seems to be a little bit greater than this one. It seems like the scales aren't quite right. These are a little more compressed, and these are a little more spread out, but we can still do it, okay? So here's what this function starts with. At 0, it's 0. At 1, it's 1. At 2, it's 2. Right? At 3, it's 3. Okay? But then at 4, it drops down to 1. And at 5, it appears to be about 0.5. Okay? So this is a straight line here, and then a curve down here. Now, mine's not very pretty, okay? I admit. Get over it. Okay? That's the graph of the function we're looking at. Okay? It says find the derivative of this function f whose graph appears in figure 8. This will be our figure 8 now. Okay, we just made it 8. At x equal 2, 3, and 4. So we want it at x equal 2, at x equal 3, and at x equal 4. We need the derivative of those functions. Okay? Now, can anyone tell me what the derivative is at x equal 2? F prime at 2. I'm sorry. So used to writing A's, I wrote an A down, even though I said 2. At 2, yeah. This function here, not the red thing, the function I'm doing there. Say again? Okay, the value of the function is 2. What is the derivative, the slope of that function? 1, yes, because this is going up 1 over 1, up 1 over 1, up 1 over 1, yeah. All along that line, it's 1. So f prime at 2 is equal to 1 because of what we did before. Okay, now, f prime at 3. Now remember what that is? Let's go back and do the actual value, okay? This would be the limit as x approaches 3, I'm going to use that definition, okay, of f of x minus f of 3. All right, Rodney's here. Hey, Y chromosome did show up today. Good, man. Okay. Still missing Richard. Okay. I guess he was here last Thursday, but he's been out for a while. Okay, over x minus 3. There, that other definition. Okay? And here we have a problem, Houston, don't we? Because the derivative of this, as x is approaching 3 from the left-hand side, from the downhill side, is approaching 1, right? So the derivative here is 1, there's 1, there's 1, and it looks like it's going to be 1 there too, right? But when you approach from this side, that is a very different slope, okay? In fact, it's not really clear what it is. It almost looks like it's an infinity, okay? So approaching from this way, it's definitely not 1. So this one does not exist because the left and right-hand limits aren't the same. You got a point there, a cusp. Not the same slope this way as you have this way. It can't exist. So this does not exist. Okay? F prime of 4. Okay? Now, without giving you much better information, it's kind of hard to see. But notice they drew that in. Now, their picture is a lot prettier than mine. And when they drew that in, they had it going right through this point and this point. The slope of the tangent line was right there. Okay? And you can calculate from the graph what that slope was. Any idea? It went through 3, 2, 4, 1, 5, 0. What's the slope of that? Going down 1 for every 1 across, down 1 for every 1 across. What's that slope? Down 1, 1 to the right, down 1, 1 to the right. -1, exactly. According to the graph, and the apparent slope there, that would be minus 1. Okay? So you see, there's really hardly any way, if this slope is constant here, and plus 1, and this is a minus 1 here, and actually it's getting less and less negative as you go down. That means it's some much smaller negative number, meaning a larger negative value, okay, going up that way. No, there's no way it has any slope there. None whatsoever. Okay? Now, sorry I didn't have this on the graph, on the slide set, but that's what they want you to do here. Okay? Now, with that in mind, what we just did was estimate a derivative. So let's see what else we can do to estimate a derivative. Now, here is the definition that we have been using. That our actual definition was f prime of a is equal to the limit as h is approaching 0 of f of a plus h minus f of a divided by h. That was our hard and fast definition, that with the limit in there. If you take the limit out, you can estimate this derivative by going just a little bit further to the right from a, figuring about what f of a is, f of a plus h is, subtract from that what f of a is, and then divide by the difference there, your difference quotient, okay? And as long as h is small, that's going to give you a fairly good definition, okay? So this is just taking out the limit and doing some small h's, but you just can't let h equal 0. And basically it's saying almost the same thing as what we said when we started off in chapter 2, when we were doing limits. This is basically going back to that same type deal. Letting the h get smaller and smaller and smaller, see what your slopes are, see if it's going anywhere. Okay? A good way to estimate. And this is exactly what we were doing before, doing again. We're always doing this when we're taking the approximating the slope of the tangent line. What we do, we take some point close where h is just a little bit greater than a, or less than a, either one, but we usually do x plus h, okay? Calculate what f of x plus h is, because we know the function. We somehow know what that function line is. Take a little bit beyond a plus h, figure out what that function is, subtract what this one is, and take the difference of these two, which is h, divide by that, that gives you the slope of the secant line. Okay? Now, it just happens to be on this function. That's an approximate value. It's not quite the same. That slope would be here, just a little more positive than this one would be. But it's an approximate value, not bad. You want it a little closer, then take your h to be a little bit smaller, like right here. Then that secant line is going to be much closer to the pink line, the tangent line, than what this one was. Okay? So when h is small, the secant line has nearly the same slope as the tangent line. Okay? Now, if this had been your P back here, and that would have been your Q, that's a terrible guess of what the slope is here. Terrible. You have to let the h be very small, so you have a small difference here, a small difference there. And if that's the case, you'll just have a small difference in your slopes. Does that make sense? Estimating what that function may be. And I think that's where example 6 comes into play. And I think these may be the tables for it, which look just like we did in the last chapter. Estimate the derivative of f of x of f of x equals sine x okay, at x equal pi 6. Okay? Estimate the derivative of f of x equals sine x at x equal pi 6. Okay? So we just calculate difference quotient. What would that difference quotient be? F prime at pi 6 would be approximately equal to what? F, which is sine of pi 6 plus some small value, h, minus what? Sine of pi 6. Okay, not h, but pi 6 divided by h. Okay, why h? This is the difference in your function, the y values, this and this. And this is the difference in the x value, the difference between this and that. Pi 6 plus h minus pi 6 will be h. Okay? Now, pick a small value. Okay? And what they did in the table is doing exactly this. Sine of pi 6 plus h minus sine of pi 6. What is sine of pi 6? 1/2. Okay? So we could just leave that off and make that a 0.5, which is what they did. Well, I lost the line. 1/2 or 0.5. And then just pick some small h's. They start with 0.01. Okay? And if you put that in there, you have to, on your calculator, do what pi 6 is. Pi divided by 6 plus 0.01. Okay? So you do what pi 6 is. Pi divided by 6. Frankly, that's going to be something a little bit greater than 1/2. Okay? And then do a plus 0.01 and plug that in. Subtract 0.5 from it. Divide by 0.01. And they came up with 0.863511. Okay. 2.001, and you get the same thing. Two digits are almost identical. 0.0001, now this is bumped up one, and that goes here. And actually what's happening, well, your slope is going to come up very close to this thing right here. Because you see, after that digit there, these digits aren't changing much. Go to the other side and do a h is slightly negative, negative 0.01. So that's going to be a little bit less than this, minus this. But then divide by h. Your h, though, remember, is negative. So even though this is negative, this is less than that, so this comes up being a negative numerator. Your h is also negative, so it comes out this again. And those aren't quite the same values. In fact, off by a fair amount there. But then while you get down here, they get a little bit closer. You get down here, they get very, very close. And here they're close to within 4, 5, 6 decimal place before you find any deviation. So 0.8660 is not a bad guess at all. Okay? Because it's the same on the left, the same on the right. So basically, I would take those two and average them. So this is how you estimate the slope. Take very small difference quotients, a difference there, and see what you get. Okay? Not a lot different. I'm sorry, I'm having trouble focusing from what we did in the last chapter. Okay? Does that make sense? Estimating slopes of a tangent line. Okay? this is basically what you've got happening there. Okay? When your first H, pretty large H, here's your pi 6, and they went H here. That's almost another pi 6. That's a pretty large H, okay? It gave you slope here. Then they reduced that pretty significantly. What did they do here? It looks like they picked the second one way down here, and that overshot it, and then you were somewhere in between with the actual tangent line. Okay? Yeah, okay. It's squeezed in between the secant lines when H is positive, that would be here, or H is negative, that would be here, and the secant line is squeezed in between those two. I mean, the tangent line is between those two secant lines. Now, obviously, the H here was much larger positive than this H was negative, because I can't even tell what that negative H was. Whatever it was considerably less. So the slope is somewhere in between those two. All right. To me, this is a lot of the same stuff we were seeing before. Okay? But just another illustration of it. So let's move on to example 7. Oh, I'm sorry. We just did example 7. Well, we didn't quite. 6 and 7 are so close to the same that I don't see any reason to go over the same thing again. It's using the formula, the definition a little more rigorously in 7 than they did in 6, but it's the same result. So there is a conceptual insight here. Are limits really necessary? And it's a nice little blurb to read, but I don't see that it's giving a whole lot more insight than what we've already done. But read through that, see if it says anything to you. That wraps up 3.1. You want to do these preliminary exercises? Preliminary questions in 3.1 exercise. Do you all have books? You don't, do you? Okay, I'll try to draw this so you can see. This is such a simple problem, it's almost embarrassing. Here's a curve, okay? And it draws some lines. Here's A. That is almost what B is. Here's what C is. And here's what D is. Something like that. My straight lines have a lot to be desired. Okay? Now, which of those lines in that figure, or something like that, are tangent to the curve? Or at least close to being tangent? B and D for sure. I mean, A and C are obviously not. B and D, at least in my pictures, are not quite, but they're close enough. I think you can say, yeah, that's right. Okay? So let me make sure they did want us to, that they weren't trying to be too nitpicky about it. This is 3.1 preliminary B and D. That's exactly what they were wanting to see. Okay? Number 2. Let's erase 1. Yeah, for those who did come in late, explained it to Nicole. I don't know what caused it. I had a treatment on Friday, which usually does mess up my immune system a little bit, but then I was working in the yard a lot of Saturday, and then Sunday morning when I woke up, my eyes was somewhat clotted up, and I've got conjunctivitis in my right eye now, and I don't know if the treatment had something to do with it. It may have, or maybe when I was pulling weeds and stuff like that, I may have gotten a little, and I was sweating like crazy. I could have gotten dirty sweat in my eye. I don't know what, but my eye just stings like crazy, so if I'm having trouble focusing, and that's part of the reason. Okay, let's move on to 2. What are 2 ways of writing a difference quotient? Say again? Yeah, the difference quotient. Since you have, you don't have a book, yeah, but yeah, you can give them to me. What are the 2 ways of writing a difference quotient? Okay, you can put it that way. You don't have to have that in front, but that is good. Is equal to the limit as what? There's 2 ways to do it. They start the same way. Say again now. As h approaches 0 of a plus h minus f of a over h. What's the other way? It would be the limit as x approaches a, no h in this one at all, of f of x minus f of a over x minus a. Your classic difference quotient. y2 minus y1 over x2 minus x1. Okay? They both are that, but the top one, instead of x, you're putting a plus h, okay? Putting that in there, and instead of a x here, you put an a plus h, okay? That stays the same, but then the h here, if, like I just said, if h is equal to no, sorry, set it backwards. Okay. What we did here is x is equal to a plus h. Okay? That's your classic difference quotient. Up here, if that is the case, x minus a is equal to h, right? Subtract a from both sides of the equation, you got h. So your f of x becomes f of a plus h. Your f of a stays exactly the same. Your x minus a, if you subtract a from both sides, you just get h. So it's just 2 ways of writing the same thing. That's all they're asking for. Okay? Let me make sure that's what they were asking for. Yeah. F of x minus f of a over x minus a, or f of a plus plus h minus f of a. They did it in a different order, but it's fine. Okay, number 3. Any questions on that before I delete it? Okay. Number 3. Find a and h. So we're looking for a and we're looking for h. Okay? Such that f of a plus h minus f of a over h, there's our good old difference quotient in one of the forms, is equal to the slope of the secant line, is equal to slope of the secant line between 3 f of 3 and 5 alpha 5. Okay? Says find the A and the H such that this thing here is equal to the slope of the secant line between those 2 points. Okay. Now they don't give you values there, they just give you representations of the values. So let's first calculate what MSEC is between those 2 points. You know what that is, right? Slope of line between 2 points. Rise over run. What's your rise? Alpha of 5, this y value minus this y value over 5 minus 3. So that would be alpha 5 minus alpha 3 over 2. Okay? Now, it says find A and H so that would have to be true. So we have f of A plus H minus f of A over H is equal to f of 5 minus f of 3 over 2. Okay? Now, looking at that, what would be your A? What would be your H? Where do you see A up in the left-hand side? There's one there, but it's sort of messed up with the H. There's also one there. So A would be 3, and H would be 2. And then A plus H would be 3 plus 2, that would be 5. All right? I know you were trying to make it a lot harder, weren't you? That's my job to make it hard. Yours is to keep it simple, right? Okay. So let me make sure that's what they were wanting in the back. But yeah, A equal 3 and H equal 2. That's exactly what they wanted. Okay? All right with that? That came from the slope of your definition of the slope of your secant line. y2 minus y1 over h2, x2 minus x1. It's just that. The difference in these two over the difference in those two. That's what your slope of your secant line is. So once you get that, and then you say that is supposed to equal that, and set them equal to each other, then look at it. That must be 3, that must be 2. Got it? All right. All right, to erase. See now, listen, just think of those poor people at home trying to follow that. This, that, they couldn't see where my fingers were going. You can. See, there's an advantage to being here, isn't there? Don't answer that question. Okay, now, let's go to 4. Which derivative is approximated by this? The tangent of pi fourths plus 0.0001 minus 1 over 0.0001. What derivative do you think that is? What derivative do you think that is? What's that? Couldn't quite hear that because my hearing's so bad. What derivative is that difference quotient representing? Okay, it's certainly going to be a tangent function. I'll buy that. The tangent where? At what a value? No, that's going to be your h. The a is going to be pi fourths. That'll be the, okay. I put tangent prime, in other words, derivative of tangent at pi fourths. Now, why is that true? Because this is a tangent at pi fourths plus a very small number minus a tangent of pi fourths. What is tangent of pi fourths? Second? What? Yeah, exactly. So this is tangent of pi fourths minus plus h minus tangent of pi fourths, 1 over h. Yeah, that's the derivative of tangent of pi fourths. Okay. All right. And that's better be what they had in the back. It's the derivative of the function f of x equals tangent x at x equals pi fourths. Okay? And I went ahead and did a notation we haven't covered yet, but I was just being lazy. Number 5. Let's go and erase this one. Y'all got this okay? Okay. Number 5. What do the following quantities represent in terms of the graph of f of x equals sine x? Okay, what do the following quantities represent? A. Sine of 1.3 minus sine of 0.9. What does that quantity represent in terms of the graph of f of x equals sine x? What would that look like in our definitions, or whatever you call it? What does that sort of look like? What part of that definition? Kind of, to me, looks like the numerator on the right-hand side, isn't it? Okay. So that would be something like the limit as x approaches, say, see which way is it going now? 0.9 of sine x. That would be what? Wait. I got my things a little backwards. Oh! Okay. I can't write down much without giving it away. The numerator here was sine of 1.3 minus sine of 0.9 over, what would be, you think would go underneath that? Wouldn't that be 1.3 minus 0.9? So that would be 0.4, right? And this would be an approximation to the derivative of sine, and again, I'm going to put that symbol there if you're okay with it, evaluated at 0.9. Okay? first derivative of, and let's see what the question is, what do the following quantities represent in terms of the graph of f of x equals sine x? Okay. To me, this thing here would represent, since that's approximately that, multiply both sides of the equation by 0.4, and that would be what this represents. Okay? So I would say 0.4 times the f prime of 0.9. Okay? It would be 0.4 times f prime, where f of x is sine x, this would be f prime of x evaluated at 0.9. To me, that's what that's saying. You see? Manipulating the definition. And this was that approximation thing, remember? That would be approximately what that would be equal. Now, I don't know if that's what they were looking for, but I think that's what I would get. The difference in height between, yeah. Okay. They want it even easier than that. It's just the difference in height between, okay, if this is your sine, and 0.9 is going to be somewhere about here, and 1.3 is going to be somewhere there, this would be the difference in height between those two. Okay, I went to a lot more detail than what they did, but that's all they were looking for, the difference in the height between those 2 points. Okay, they were even looking simpler than I was thinking. What would this represent to you? That was the A part. The B part. Sine of 1.3 minus sine of 0.9 divided by 0.4. Okay. Now that we just answered, okay, that would be the, that's the difference quotient, okay? That would be basically a different points on the graph here, that would be the slope of your secant line between these 2 points, right? This is the difference in y over difference in x. That's the slope of the secant line. You see it? Okay. That better be what they have in the back. If not, I'm going to scream. The slope of the secant line between 0.9 sine 0.9 and 1.3 sine 0.3. Exactly. Okay? And then the C part. The C part is f prime of 0.9. What does that represent? Of that function there. Whereas the difference quotient gives you the slope of the secant line, what does the first derivative give you at a certain point? Say again? The slope of the tangent line at x equal 0.9. That better be what they have, the slope of the tangent line at x equal 0.9. Very good. All right, got those done. Homework exercises here. Do number 1. Do any of the odds 3 through 7. Do either, do either 9 or 11 or both. Okay? And if you had to do one, I'd say choose 11. But if you want to do both, do those. Okay? Then do either 15, 13 or 15 or both. Either 17 or 19 or both. Any of the odds 21 through 27. Okay? Eye is stinging like crazy. Do any of the odds 29 through 45. And I would do 47, well, let me say, any of the odds 47 through 51. Then any of the odds 53 through 57. And any of the odds 59 through 65. Now, some of these say you need a graphing utility. If you don't have one, don't sweat it. Don't get too bogged down with it. Then any of the odds, 67 to 73. And that'll pretty much wrap it up. All right. Any questions? It's 3.1. All right, let's move on to 3.2. I don't know what it's doing here. No. Okay. For some reason, this has gotten off. Okay, here we go. Okay, for some reason, it's having a hard time opening 3.2. I don't know what's going wrong here. There it comes, maybe. Still having a hard time opening. There it comes, finally. All right. All right, we're starting, any questions on 3.1? Okay, we're starting 3.2 just about where we left off. Was that the door? Huh? Okay. I thought I heard the door open. My hearing's so bad. In the previous section, we computed the derivative f prime of a for specific values of a. It's also useful to view the derivative of a function f prime at whose value x equal a, seems like that's saying the same thing, is f prime of a. Okay. The function f prime is still defined as a limit, but the fixed number a is replaced by the variable x. So rather than what we were using a's before, and this is what I was jumping to, and I realized I was jumping ahead, f prime of x is defined to be the limit as h approaches 0 of f of x plus h minus f of x over h. Remember, I had you doing one, and I said, wait, go back and put in a's there. This is the definition of a limit. At any value x, not just at some specific value x equal a, at any value x. Okay? Now, a couple of other things, and I hope you don't find these too confusing. They can be at first. After a while, you get sort of used to them. Okay? And that's this. We call that f prime of x. Sometimes we say, of course we say y is equal to f of x, right? So sometimes, since we're then talking about f prime, well, sometimes we call it y prime of x, okay? That will not be another way that we refer to it, or just simply y prime, or, like we did here, f prime of x. So we have a bunch of different ways to refer to the first derivative of a function. If we've already said that y is equal to f of x, we can call it y prime of x, or f prime of x. All those mean the same thing, okay? So don't let the nomenclature fool you, okay? Try to keep it straight. Now, they have a little margin note at the top of page 122. Often the domain of f prime is clear from the context. If so, we usually do not mention domain explicitly. Okay? So that's a little caveat we're going to throw out there. Most of the time we don't talk about it. But every now and then we will have to talk about it. So when we do, you'll usually see. The domain of f prime consists of all the values of x in the domain of f for which the limit exists. That limit right here, this one that's on the board right there, okay? We say that f is differentiable if that limit exists, okay? If that limit f prime exists for all x's on the interval a to b for which that's true. When f prime exists for all x's in an interval or intervals on which f is defined, we say that simply f is differentiable. Again, nomenclature, what we're saying. So let's do example 1, and I think example 1 may refer to this. Yes, it does. Okay? So let's blow it up to begin with. We won't keep it long because we're going to write on it. Okay? But here's your function. Prove that f of x equal x cubed minus 12x, that one you see right here, is differentiable. Okay? Well, how do we prove that? We prove it by taking that derivative. Okay? It's actually computing what f prime is. Now, what's the definition of f prime of x? Just had it on the board a little bit ago. What was it? The limit as h approaches 0 of f of x plus h minus f of x over h. Now, unfortunately here's our f, okay? So the first thing we got to do before we can plug it into this limit is figure out what f of x plus h is. Okay. There are easier things, but it can be done. So let's do it. F of x plus h. Got to figure out what that is. What would you say it is? How would you begin? Okay, don't worry about derivative yet. Let's do what f of x plus h is. There's our derivative. There's the definition of it. So we're going to have to first calculate what f of x plus h is. What is this given f of x is this? Okay. Everywhere you see an x here, you plug in instead of x plus h. Remember? So what would that be? X plus h raised to the third power minus 12 times x plus h. That looks pretty simple, doesn't it? Except we got to cube x plus h. Now, that's not a super easy thing, but it is probably easier than you think it is. How would you cube x plus h? You tell me. A second. Yeah. Yeah, you multiply it by itself 3 times, okay? So that's going to be x plus h times x plus h times x plus h, okay? Now you want to do the first 2 first and then multiply by the third, or do the first times the next 2? It doesn't really matter. Which way would you do it? First 2? Okay. What would they give you? X squared is 2xh, right? Okay. Plus h squared. And you'll take that and multiply it by x plus h. Remember, it's the first times twice the product of the 2 times the second. The first squared, twice the product of the 2 plus the second squared. Okay, now doing this one, do it a term at a time. Okay? X squared times x is x cubed. Then do x squared times h is plus x squared h, right? Okay. You did first term, it's sort of like flowing only you have too many letters. First one times this, first one times that. So x squared times x is x cubed. X squared times h is x squared h. Right? All right. Now, let's go to the second one. Let me do this in a different color. You pick a color for me. Green. Light or dark? Light. I thought she was going to say that. Okay, there we go. So this time we'll do this one times that, and that's going to be plus 2x squared h, right? And then this one times that. And what does that give you? Plus 2 x h squared. Okay? Now let's go to the third one. Let's do a different color for that one. What color? Second? Light or medium? Okay, how about the light, since we did light green? So now we'll do the third times that, and that's going to be plus x h squared, and then third times second would be h cubed. Now we're going to add all those together. I want to go back to our dark color. Okay, that'll be an x cubed plus 3x squared h, right? 1 here and 2 there. Here. Plus what? 3xh squared plus h cubed. Okay. Now my next question to you may seem really out of the blue. Have any of you ever heard of Pascal's triangle? You have. Okay, you remember how that goes? Okay, start with a 1. And then we'll do 2 more 1s. And then we'll do another 1 on the outside, but here we'll add those 2 and make it a 2 and a 1. Always 1s on the outside. So this next one would be a add those 2 together. 3, 3, 1. The next would be 1, 4, 6, 4, 1. You keep on going as many times as you want. This gives you the coefficients of a binomial expansion. There's a binomial. This is x plus h, say, raised to the 0th power. That's 1, right? And x plus h raised to the 1st power is just going to be x plus h. 1x plus 1h, right? Right? And x plus h squared is going to be x squared plus 2xh plus h squared, right? That's what we did right here. Those are your coefficients there. 1, 2, 1. And then for the x plus h cubed, 1, 3, 3, 1. 1, 3, 3, 1. So once you get your coefficients from Pascal's triangle, then your variables are going to be x cubed h to the 0, x squared h to the 1, x h to the 2nd, x to the 0, h to the 3rd. So you're decreasing your x's every time, increasing your h every time. That's another way you get it. Or you can do it the way we just did. Both of them work. Okay? So there's your alpha of x plus h. Well, no, that's the first part. Okay? So here's what we have. X plus h would be x cubed plus 3x squared h plus 3x h cubed plus 8, xh. This thing drives me nuts. Okay. xh squared and xh cubed. That's the first part, minus 12x minus 12h, right? There's your alpha of x plus h. You buy that? What we did was just this part, but then we still had this part to add to it. So that's what we put up here, the limit as h approaches 0 of this thing, x cubed minus 3x squared h, that's plus, I'm sorry, plus 3xh squared plus h cubed minus 12x minus 12h, that's your alpha of x plus h, minus alpha of x. Well, here's your alpha of x cubed minus 12x, right? Divided by h. You just plug in what alpha of x. This is alpha of x plus h, that thing, minus this thing, that's that. And now you see, this is a lot of writing, but it's the limit as h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus 12x minus 12h minus x cubed plus 12x, all divided by h. Can we eliminate anything yet? Here's an x cubed, there's a minus x cubed. They go out. Here's a 12x, there's a minus 12x. They go out. I hate to write all this again, but well, what I'm going to do is erase Pascal's triangle, if that's okay. Y'all got it? Blaise Pascal, by the way, was the one who came up with that. Good paper topic if you haven't chosen one yet. Either who was he, or how did he develop that, or why did he develop it, or applications of developing, or whatever. So here's the limit as h approaches 0. Now we got rid of some terms, and what we have left is 3x squared h plus 3xh squared plus h cubed minus 12h divided by h. Now what do you notice about that numerator? They all have a factor of h in it. So let's factor that out. That'll be the limit as h approaches 0 of, let's factor out the h, and that leaves us 3x squared plus 3xh plus h squared minus 12, right? Divided by h. And guess what happens? The h's can go out now. They've been dating. No, okay. And now we have the limit of this thing as h's are going to 0. As h gets close to 0, that goes close to 0. That really goes close to 0, and you're left with 3x squared minus 12. That's the limit as h approaches 0. That's your f prime. That's your f prime of x. For that function here, there's your f prime. Okay? Now, what's that? Yes. You know the short way, don't you? Yeah, and isn't it the same? Right, and isn't that the same thing? The short way is take the exponent, multiply it by the coefficient, drop the exponent by 1, that'd be 3x squared minus 1 times minus 12, drop that by 1, you get x is 0, which is 1. So you get 3x squared minus 12. That's exactly it. We just showed why that's true. You took the limit, that's what you get. Okay? You're cheating, aren't you? Okay, now. And that's all I asked you to do. Oh, no, it didn't. It said compute f prime. We did. Okay? Then find an equation of the tangent line at x equal negative 3. Find the equation of tangent line at x equal, was it 3 or minus 3? I have a good memory. Minus 3. X equal negative 3. So we want an equation of a tangent line. Anyone remember what that equation of a tangent line looks like? How you get it? Okay? Yeah, first thing we're going to do is f prime at -3. And what would that be? Three times, again, we're just plugging in what's inside the parentheses. What's -3 squared? 9 minus 12. What's 3 times 9? 27 minus 12, and that's equal to 15. So there's your f prime of -3. What is that? Your first derivative is your slope of the tangent line, right? Okay. So now we got the slope. We want the equation of the tangent line. Okay. Now, okay, I think what you just said was plug this into your equation to get your y at this value of x, right? So f of x equal y, right? So let's do that. F of -3 would be -3 cubed minus 12 times -3, right? Plugging into this one, right? Okay, and that would be what? What's -3 cubed? -27. And what's -12 times -3? Positive 36, and this comes up being 9. Okay, so f of -3 is 9. Okay, so this is your, okay, if you want to call this, you can call this x1, and you can call this y1 if you wanted to. And this was your slope, this was your m, right? So you want the equation of the tangent line. That's the slope of the tangent line, okay? This is the point at which you're doing that, so you use the point slope formula. Remember that one? Y minus y1 is equal to m times x minus x1. Now, if you find that formula, I just don't want to remember all these formulas. I bet you remember the formula for a slope, don't you? Formula for slope is y2 minus y1 over x2 minus x1, right? Rise over run. You remember that one, right? Well, here's what we do. This is if you know the 2 points and are looking for the slope, that's what you use. If you know the slope in 1 point, all you do is take out the 2's here, okay? And then you multiply both sides of this equation by x minus x1. And what do you have? Y minus y1 is equal to m times x minus x1. You just get it right from there. And now you plug in. Y is a variable, don't change it, minus your y1 was 9 is equal to m. We calculate what m was, that was 15, times x minus, and the x1 was a -3, so that makes x plus 3. There's your slope of the tangent line. You can clean it up a little bit if you want to. Y minus 9 is equal to 15x plus 45. So that would be y is equal to 15x plus 54. There's your slope of the tangent line. At least I sure hope so. Yep. Y is equal to 15x plus 54. Yeah. Now, here is where they did. Here they found the point. This is where they plugged in here. Put in a -3 here. Calculated that to be a +9. Now let me tell you, This doesn't look like that's the slope of 15, does it? Look at this. There's 20 on the y-axis, that's 2 on the x-axis. This is really a compressed y-scale and expanded x-scale. But this is the point, negative 3, 9. When you plug that in, here's your slope of the tangent line that we got from our derivative, 15. And when you plug that in, that's your equation for the tangent line. All right, we just did example 1. We'll start next time with example 2. Let's see if we got far enough to have any homework exercises. I think we did, but not very far. I think you can do any of the odds, 1 through 5, and stop there. We'll do the power rule next time. You've already been doing the power rule. Okay, so just do any of the odds 1 through 5. Good deal. Any questions? 3.2 so far. We're really getting into the fun stuff now. All these limits just sort of, but yeah, it's all fun though, right? Yeah. Okay. All right, we'll see you Wednesday.